Friends, in this video I'd like to solve the following problem from the United States of America Mathematical Olympiad, USAMO, 2002, problem number 4. We want to find all functions f from the set of real numbers into itself, such that f of x squared minus y squared equals x times f of x minus y times f of y, for all real numbers x and y. So it's a classical problem from functional equations. Here are my hints. First, set y to be 0 to show that f of a minus b equals f of a minus f of b for non-negative numbers a and b. Then prove that f must be odd. And then, in preparation for the last part, show the following two equalities, that f of y plus 1 equals f of y plus f of 1, and f of 2 times y equals 2 times f of y for non-negative y's. And finally, set x to be y plus 1 and try to write this in two different ways. I'll give this problem a try and I will see you in just a minute. Oh, sorry. Okay, so let's tackle our problem. As I suggested, let's start with setting. Set y equals 1, 0 in our condition, which I mark asterisk. Then we have the following: f of x squared equals x times f of x. Okay, and using that, our condition asterisk can be rewritten as f of x squared minus y squared equals, instead of x times f of x, we can put f of x squared. So f of x squared minus f of y squared. But notice that x and y are arbitrary, so we can get any non-negative numbers here and here whatsoever. So we can say for every non-negative numbers a and b, f of a minus b equals f of a minus f of b. Very well. In particular, setting b to be 0, in our condition, which I mark maybe square, then we have the following. F of, maybe not, let's set not b to be 0, but let's set a to be 0. Then we have the following: f of minus b equals minus f of b, i.e. f is odd. Our function is odd. Moreover, let's set a to be b plus 1 in our condition square. Then we have the following: we will have f of 1 equals f of b plus 1 minus f of b. In other words, f of b plus 1 is f of b plus f of 1. Of course, that only holds for non-negative numbers b. And finally, we will set one more variable. I will set a to be 2 times b in our condition yellow square. Then, if I set a to be 2 times b, then I have f of b equals f of 2 times b minus f of b. In other words, f of 2 times b can be written as 2 times f of b for every non-negative number b. Very well, very well. And now, what we will do, we will set x to be y plus 1 in our very first functional equation, in this one, we will get the following set in this equation. Then we have the following: f of y plus 1 squared minus y squared equals f of y plus 1, f of y plus 1, f of y plus 1 minus y times f of y. And maybe let's write it explicitly that I assume for now that y is non-negative number. Very well. Now, on the left-hand side, after simplification, we get 2y plus 1. And on the right-hand side, the right-hand side can be written in the following way: y plus 1. Instead of f of y plus 1, using this condition, we can write f of y plus f of 1 minus y times f of y. And the left-hand side, on the other hand, can be written as 2 times f of y plus f of 1, using once again this and that. And if we multiply the right-hand side, we have y times f of y plus y times f of 1 plus f of y plus f of 1 minus y times f of y. And that's perfect because now we have a bunch of cancellations. For example, f of 1, gone. Y times f of y minus y times f of y, gone. Here we have 2 f of y, and here we have 1 f of y, gone. And finally, what we are left with, after all of that, is f of y equals y times f of 1. And remember that that holds for every non-negative number y. What about negative y's? Well, notice that our function is odd. F is odd. So for every non-negative number y, non-positive number y, sorry, f of y can be written as minus f of minus y. And now minus y is non-negative, so it can be replaced by this as minus y times f of 1, so it's y times f of 1. In other words, our function is linear. So f of x equals c times or a times x, let's say, or some constant a. Very well, and now let's do verification. We need to verify that every such function satisfies our equation. Verification is very straightforward. On the left-hand side, we have f of x squared minus y squared, which is a x squared minus y squared. And on the right-hand side, we have x times f of x minus y times f of y, which is x a x minus y a y, exactly the same. They are exactly the same. So now we know that our solution set consists of linear functions. And that closes our problem. Very nice functional equation. Thank you very much for watching. I will see you next time. Goodbye.